Hey, I actually had a question.
Yeah, go for it, Taylor.
So I sent an email to the testing center and they never actually got back to me. I don't know if I sent it to the wrong place, but I remembered you saying that you had availabilities, I think at 3 on Wednesday.
Uh, Not at 3. The latest I could do it is 2. I might have said 3 by accident, but
Okay.
my schedule
Um,
doesn't allow it any later than maybe 2 o'clock.
okay. I'm in high school actually, so I have class until 2. I
Gotcha.
can probably get out early to come. I think it's about 20 minutes from my high school, so I can probably make it.
Yeah, that shouldn't be a problem. It'll be in either JC 26 or JC 21. So you just show up there, and it's going to be technically on the computer, and
Okay.
I have to leave a little early that day, but I have someone that's proctoring for me. So if you don't see me, there might be someone else there.
Okay, but do you want me to send you an email to get it like so you have it on the register, or do
Yeah,
you want me
yeah,
to
if you
just show
just
up?
let me know, yeah, send me an email just so I have a record of that, and
Okay.
then that way I'll keep track of who's coming and who's not. But I appreciate that, Taylor.
Yeah. And then did you say you had a later one on Thursday? That
Oh
way
yeah,
I
Thursday it's actually I think earlier, not later.
Oh, okay.
It's like
Then I'll do
9:30 in
it
the
to
morning.
2 o'clock. Yeah.
Yeah, and
All right.
that starts. Let me see. Yeah, that one starts at 2. I have some students starting at 1:50, but that's about the latest. But if you the only problem is if you show up late, you won't have the full hour and a half that I'm giving everybody.
Yeah. That makes
But
sense.
most people don't take that long. It only takes about 40 minutes to take it.
Okay.
All right.
Thanks.
No problem. Thank you, Taylor. Hello, everyone. Two more people came in. I see you're now chatting your first and last name. That's helpful. I appreciate that. Feel free to ask me questions as you have them. We do have a test supposed to be getting done. It was supposed to be done by Wednesday of this week, but I've now allowed you guys even a little later just because we had some problems that were partly my fault and some problems that were just things that happen. So don't worry about it. And anyways, we'll get on the ball. The problem is when I keep it this late, that means your next test is going to come pretty quick after this test. So that's the only downside.
I was having some issues with terminal velocity just because it wasn't really clear about what the B value is.
Gotcha. So, yeah, that's actually what I'm going to cover today. I thought I
Okay.
made is the homework's not due till tomorrow, right? Or the next day or
It's
something.
yeah, it's not due till tomorrow.
Yeah. Yeah, I'm covering that in a few minutes. I'm going to do an
Okay.
example for the centripetal accelerator or for the general acceleration, and then I'm going to do an example on uh, terminal velocity. The B is something they have to give you though.
All right, because in the practice test, like they generally didn't give you the B. I was going through like the practice quiz, and whenever one involvement that came up, they didn't really give you the B. They always was just say it's like like generally they'd say it was like based on how far you're falling, but it would never actually tell you what the B was.
Gotcha. There's ways you can word the question where you don't actually technically have to know the V, but yeah, they should give it to you. Basically, the law that they're doing here is that it's a Navier-Stokes, if I remember correctly, and when you go to see what the terminal velocity, or excuse me, what the drag force is, it's proportional to the cross-sectional area of the body that's falling and proportional or related to the density of the fluid. And then there's like a constant or something in front of that. But technically speaking, they're supposed to give you the quantity for B, or at least the quantity for the constant that would go in front of the cross-sectional area and the density of the fluid and all that good stuff. But we normally just ask, something along the lines of if the if the terminal velocity, or let's say if the drag force is X newtons at 30 meters per second, what's the terminal velocity? That allows you to get what the V is because you know that the drag force is B times V. So if they give you a number for force, then you can solve it for B using the V and the force they gave you. Then the drag force become or the terminal velocity becomes BV over mg,
Yeah.
and you've already figured out the B, so that's where that comes from. So they sometimes can trick you or seem like they're trying to trick you by letting you know that they're not going to give you the B, but they gave you something to find the B.
Yeah, I noticed several trick questions on it on in the practice quiz where it's like, hey, switching like the whole hours to kilometers one, but only
Yeah.
one of them is actually squared and the other one isn't.
Yeah. They're trying to get you to pay close attention. It does definitely seem like a trick question, but it's really part of it's they're trying to get you to pay close attention. Part of it's they're really wanting you to notice details and recognize certain things about units, that sort of thing. But yeah,
Yeah.
sometimes it just feels like a mean trick.
Yeah. I also for one of the significant figures questions, it was like how many what is significant figures in 426,000
hmm
and
That one's
it
ambiguous. The
yeah,
answer's
that was like this
ambiguous.
is that because there's not a period at the end that the answer turned out not to be six? Because I put in six, it was like that's not it. It's like,
Yeah,
what do you mean
that's
that's
one
not
I've
it?
been hinting at in my videos as well as my lectures in class because and I've made a couple statements about that. Giancoli makes a very specific definition about sig figs when they're numbers like 5,000 or 427,000 or something like that. He says it's ambiguous, and that technically is right. But the way I define my sig figs is if there's no decimal there, you can't count any zeros. So the 426,000 would only have three sig figs.
Yeah, I forget if I put six or three, but either way, it said it was wrong. So I guess it was like impossible to tell is the answer.
Yeah, if you read, it's in the next to the last section or one of the early sections of chapter one in Giancoli's book. He makes a point to tell you that it's ambiguous when someone says the number 5,000 or 500 or 50. It's ambiguous, and that's who wrote the questionnaire. That's why I've repeatedly tried to tell people.
Yeah.
That being said, even when I repeat it, nobody necessarily notices. So I've been trying to hint at that, and hence it's on this video now specifically so everybody would know, hey, if a number like 5000 pops up in your online practice test or your actual face-to-face test or your actual online test, then you should answer it like they taught you in Giancoli, which is that the number 500 or the number 5,000 or the number 426,000, those numbers all have an ambiguous number of sig figs.
Okay.
But add that one little dot, and then according to my rule, it would clearly be, the full, all the numbers are significant
Six.
if it's 425,000, period.
All right. Thank you.
No problem. I'm glad you asked about that. It gave me another chance to say it in the right context. There's another one that a lot of students had a hard time with. I've tried to mention that a couple times, and it was like a number like what's the percent uncertainty for the number 5.6 or something weird like that. Have y'all seen that one? Or have you seen it?
Um, the 5.6 plus or minus like 1.5 or something.
If they have that, it's not so difficult, but sometimes they'll ask you something like, what's the percent uncertainty of a number 4.9, and they don't give you a plus or minus. What you're supposed to do in that case is you assume there's a 1 plus or minus 1 in the last digit. So if someone says 46.9 and they ask you what the percent uncertainty is, you're going to take point 0.1 because that's a change of 1 in the last decimal place, and you're going to divide that point 0.1 by 46.9, and that would be the decimal uncertainty, and then you move the decimal two places to the right to make it percent uncertainty.
Okay.
So yeah, keep that one in mind too, because I like those questions, but I really have to tell you guys to you're supposed to get it from your reading, but just in case you miss, here's the answer. So hopefully
Yeah,
that'll help some people.
yeah, I have the test tomorrow, so I
Awesome.
gotta be careful
You'll
about that.
you'll probably do a lot better than you think you're going to do, and don't
Uh,
stress too much if it turns out low, because normally the first one's really really low. It's not uncommon for me to have a test average on the first face-to-face test that might be in the low 50s. I mean, that literally happens sometimes. So if you get that, be advised that probably the class average is very low, whereas if you get a
okay.
decent score, it's probably the class average is a little higher.
Okay.
Okay,
Well,
so
About the
hopefully it's not too bad.
face-to-face. Oh, sorry.
yeah, yeah, just don't have a heart attack. You'll be good. Who was that asking this next question?
That's Taylor
Go ahead,
Mitchum.
Taylor.
I asked earlier about the
Taking the
proctored
test. Yeah.
for you. Would you rather I just respond to the last email that you sent? That way it's kind of categorized for you already. or if
Yeah,
you
that's
want me to just
fine.
send it
That's fine
individually.
too. Normally, my rule is when you do reply, you're supposed to change the subject line, but you can reply to it either way. And the
Okay.
fact that you told me, I'm going to look for it anyways.
Okay. Should I just write 241 night at the top of the thing just so you,
Yeah,
or is
that
it
would help.
okay?
Yep.
Yep. Sounds good.
Appreciate it. Anybody else have any questions? Now, again, like I said, there is a high probability, maybe a middling probability, say 30% chance that the class average on the first face-to-face test might be in the low to mid 50s. And that's the more important figure when you're taking college level physics or college level chemistry or something like that. So keep that in mind, guys. Don't stress out too much. Don't think it's time to drop or change your major or something like that. I literally get people fretting that every time the first test occurs. And to be honest with you, I literally had the same thing happen to me when I was working my first homework assignment in my PhD program, and I was bothered that there was 23 problems we had to solve, and one of them I just could not get. And I told the instructor, I said, I don't know. I'm starting to worry that maybe I'm not cut out for a PhD. He said, do you think you shouldn't be in a PhD program because you can't solve one physics problem? And I said, well, yeah. I mean, this is, bread and butter physics. And he's like, no, it's not like that. So just keep that in mind, folks. Don't stress yourself out harder than it needs to be. There are things that count in addition to your grades. So one bad grade's not going to kill you. And I'm going to work really hard to make sure y'all understand if you have any other problems throughout the semester without being able to do well on the face-to-face test. Or the big thing, a lot of people complain because their homework grade is bringing their lecture grade down with these classes, especially the online ones. But all of them are that problem. But what I want to let you know is at the end of the semester, usually about 3 or 4 weeks before the semester's over, I give you a way that you can improve your homework tests or your homework scores so that they won't bring your grade down. I don't like to tell you much more than that, but just know that towards the end of the semester, I'm going to give everybody an opportunity to correct the problem that their homework grade might be pulling their grade down. So if your homework grade is the low mark amongst your test averages and your online test averages and your face-to-face test averages, just know that I'm going to provide some way for you. And it's not too onerous. It's not like a lot of work you got to do. It's just something that I do every semester to help my students. So I'm here for you. I try to pay close attention to my students. I care about them a lot, and all I want them to do is learn. I don't want them to learn a lesson about, getting eliminated from a program or anything like that. I want them to learn a lesson about how to learn. Anybody else have any questions? All right, we're getting a lot of people coming in now. This is nice. Excellent. Already up to 9 students. Woohoo! Ooh, another one came in. 10 students. Actually, technically, it's nine
Hi,
students.
I have a quick question.
Go for it, Noah.
So I understand on like the practice tests that some of the questions are on the test, so I understand not showing the answers for those. That makes sense.
Mm-hmm.
But on like the chapter practice, because I was doing the practice test for the face-to-face test, and it's just if I get something wrong, it's really hard for me to understand what the correct answer is because I can't see it.
Right.
Is there any way that you could make at least the chapter practices where we can see the answers?
I can't because they're all coming from the same bank. But on a case by case basis, at any time you have a question that you want answered, I will work it out for you to make sure you know the answer. I can look up the answer. I just try not to make it, published. Like I would prefer not to give the answer on a video, for instance. But more importantly, I definitely prefer not to have something where they could easily make a picture of the photo. But yeah, if you ever have a question, you just don't know what the answer is, and you've thought it was a couple different things and both of them got wrong, that's a good time to ask me. And I can either just tell you what the right answer is, or I can help you work it out and then show you what the right answer is and stuff like that. So yeah, I'll do that on all of them. But the main thing is not only are the questions in the practice test and the chapter quizzes, not only are they 80% of the course material or 80% of the points that are going to appear on your face-to-face tests, the last couple decades, I have not even added an additional question. So they're literally 100% of what's going to appear on your actual test.
All right, gotcha. Thank you.
No problem. But yeah, I get it. Every semester people want that. So feel free, send me a text message, take a picture of the actual problem with the answer choices. Say, hey, I really can't figure out this one. What is the answer? And I'm just asking that you not share it because that sort of defeats our ability. There's literally a limited number of problems that we can assign as physics instructors that you can actually solve numerically without, having to write computer code to solve it. So we don't like just randomly giving out the answers to all of them. So I ask as a, on your honor that you not propagate it and send it out on the internet and stuff like that, but I'll gladly answer them for you.
Yeah, absolutely. Thank you.
No problem. All right. Well, it's 5:31, so I guess we should go ahead and get started. Most people have already texted me or chatted me your first and last name, so by all means, go ahead and do that if you haven't done so already. Again, that's how I check your attendance and keep track of that. I wanted to mention to you that I got a couple problems that I need to address with regards to chapter 5 before I jump into chapter 6. Chapter 5 is on the centripetal acceleration and the friction forces, but they're still just applications of Newton's second law. What I hadn't covered is an example on acceleration in general, because you can accelerate by turning your steering wheel of your car, and an acceleration there can be centripetal acceleration to maintain a circle, but you can also hit the accelerator or you can hit the brake, and both of those cause you to speed up or slow down without necessarily changing direction. So ultimately, there's a total acceleration that can take into account both your speeding up, slowing down, and your changing of direction, and that's the kind of problem I want to work. Last time I did do an incline, a banked curve, and worked it out, and to get you started, basically considering friction with the incline. And then I let the friction force go to zero so you get the regular formula. But that was just me making sure you had some idea of how to go about finding out if you wanted to make use of friction, how would you bank the curve? So check that out. Anybody have any questions before we get started? I'm going to go ahead and share my screen otherwise. Okay, looks like we're good, other than the fact that we still got people coming in, which is good. I'd rather them come in than not. So I'm going to set my screen to iPhone, iPad. Okay. So first off, I'm turning to example 516. So let me say example 516, and this is straight from your book. I'm going to read it to you, but you can also refer back to your textbook for the actual wording and all that good stuff. But it says a race car starts from rest and accelerates at a uniform. There I go with the yawn again. A race car starts from rest and accelerates at a uniform rate of speed of 35 meters per second in 11 seconds, moving on a circular track of radius 250 meters. Assuming constant tangential acceleration, find A, the tangential acceleration, and B, the radial acceleration at the instant when the speed is V equals 15 meters per second. So as I read that, I was trying to think, like we always do, what are these numbers and how can I tell what they are? I look at the units and what symbol do we normally associate with each of these numbers. So, for instance, it said a car starts from rest, so that tells me the initial velocity is 0 meters per second and accelerates at a uniform rate to a speed of 35 meters per second. Notice I kind of flubbed up that statement when I was reading it the first time. A race car starts from rest and accelerates at a uniform rate to a speed of 35 meters per second. So that means the final velocity is 35 meters per second, and it also means that the acceleration is equal to a constant. So I'm just going to put that there. Remember, acceleration being a constant is what we learned in chapter 2 that when that's true, then we can integrate A being a constant equals dv dt. And when we integrate that, we get v, the final velocity, is equal to v0, the initial velocity plus at. And then we can put that put that v equal to dx dt, integrate that, and we get x equals 1 half at squared plus v0t plus x0. There's also another equation that is true when the acceleration is constant, and that's v0 plus v1 over 2 is equal to the average velocity. Those three equations are only true when the acceleration is constant, and what they just told us was this acceleration was constant. That being said, we're not using much of those equations, but I just want to let you know that's what it meant. They're going to say that it goes from 0 to 35 in a time delta t, which equals 11 seconds. And it's moving on a circular track whose radius, and since that's an actual number radius, I used capital R, and that's 250 meters, which I'm going to assume is 3 sig figs. I think, again, as we were talking earlier, this is one of those cases where Giancoli and therefore our test banks would say the number 250 has an ambiguous number of sig figs. It could be 2 or it could be 3. But in this case, like I said, I'm going to go ahead and force it to be 3 sig figs by putting a decimal place and then putting a 0 with an underbar after it, showing that that one's not a sig fig. The other thing that they wanted us to know is, assuming constant tangential acceleration, find A, the tangential acceleration. So A tangent is equal to dv dt is equal to question mark. And then part B, they want to know the radial acceleration. So we're going to say AR equals question mark when V is equal to 15 meters per second, like that. Okay, so that's all the numbers we had. I'll read it one more time. A race car starts from rest and accelerates at a uniform rate to a speed of 35 meters per second in 11 seconds, moving on a circular track of radius 250 meters. Assuming constant tangential acceleration, find A, the tangential acceleration, and B, the radial acceleration at the instant when the speed is V equals 15 meters per second. So, solution. A is equal to dv dt. When we integrate that, we actually do get one of the equations that I mentioned that we wouldn't necessarily need, and that equation is v is equal to v0 plus at, but that is actually the same thing as the average acceleration formula, so that's v minus v0 over in this case, I'll call it delta t since I called it delta t before. So that's going to be our A tangential. That's what this A equals dv dt is. The A radial is going to be what we called A centripetal, and that's V squared over R. So we'll start off with part A, and we're going to say A tangent is equal to, in this case, we're going to take V final minus V initial and divide it by delta t. That gives us 35 meters per second minus 0 meters per second divided by 11 seconds. 11 goes into 35 three times. That makes it 33. So we have 2 left over. And 2 divided by 11 is 1.9 or 0.19, because 1 over 11 is 0.0999, something like that. So hopefully that should work out to be 3.19, and that's 1 extra sig fig, but that's meters per second every second, and that's A tangent. Again, I do a lot of neat little things to try to avoid having to pull out my calculator. That is not part of the course. You don't have to do that. Not only that, I make mistakes. So if you're calculating along with me, that would be really great for you to correct me when I make an error, because I make a lot of them doing the arithmetic like that. So now we're going to go on to part B. Oops. And for part B, what we have is A radial is equal to A centripetal, which equals V squared over R. And this time we're using the 15 meters per second. So it's going to be 15 meters per second squared over 250 meters. Now 15 squared is 225, and that comes out to meters squared per second squared. Got another person coming in. And 225 divided by 250, you can see that in fact that's something that 25 goes into both of them. In fact, we could call this 25 times 25 goes into 225. It goes 8 times to 100, so this would be times 9.
Um,
Yes.
excuse me, where did you get the 15 from?
Where they said, what is the radial acceleration when v equals 15 meters per second?
Oh, okay. Sorry.
No problem. So I'm calling the 225 25 times 9, and I'm calling the 250 25 times 10 meters, like that. And you can therefore see that the answer is 0.900 meters per second. So A radial in this case would be 0.900 meters per second every second. So that's the other answer, but I really want you to understand that this is a acceleration that's a vector quantity, and the acceleration total, therefore, A total, if I expressed it as a vector, it would be A tangential times some tangential vector that's made into a unit vector. So whenever I have a little hat on a vector, that always means a unit vector, like I hat, J hat, K hat. In this case, I just said T because it's a tangent vector. And then I'd say it's also a radial times r hat. In that case, I'm saying a radial vector, which points, normally you would say radial points radially outward, but you could define it to point inward. The main thing is, in this case, it's inward, so we're going to use the radial to point inward, but that's really what the vector is. And that would suggest, for instance, that we're looking at 3.19 meters per second every second times the tangential vector plus 0.900 meters per second times the r hat. So to express that truly in terms of a vector, what you want to do is draw a coordinate system. In this case, I'm going to point radial. I'm going to assume radial points towards the center of the circle, which in some sense would be downward for this diagram. So I'm going to call this the radial direction. I shouldn't put that hat on it though, but that's the radial direction. And what we know is we've got a vector that's about 3.19. So I'm going to say right about there. And then we've got that's the tangential one. Then we've got a radial one that's about 0.9. So I'm going to say that's about here. And this one's 3.19. Right there. I'm leaving the units off, but the main thing is the resultant vector is this guy. And I'm going to call this angle right here, I'm just going to call it phi. You can call it anything. You can call it theta because that's normally what we use, but sometimes I like to mix it up and use some other Greek letters, so that's all I'm doing here. That means the total acceleration is given in magnitude by 3.19 meters per second every second quantity squared plus 0.900 meters per second quantity squared square root. Now you got to be careful with the sig figs whenever you're doing a square root. It's important that you take it multiple steps to check your sig figs. If you have a class where, like mine, where the lecture material, it doesn't matter too much about the sig figs, then it's not a big deal. But when you go online and you do online homeworks, they inevitably, even when I try not to try to set it in such a way that you don't get penalized for bad sig figs, it still grades you a little bit on sig figs. So I just telling you again how to actually keep up with this. So what we're going to do is realize that 3.19 has two sig figs. So I'm first going to square that and see what that number looks like. 3.19 squared gives me 10.17. So that's going to be the square root of 10.1. I'll just call it 176. Now, it was only two sig figs, so that means only the 1 and the 0 are significant. And this is meters squared second to the fourth. And now I'm going to do the same thing for point 0.9, which obviously you know is going to turn out to be 0.81. And that means plus 0.81. Now, that was only two sig figs as well. So that means a third decimal place has no sig figs. And this is not a sig fig, I should say. And this would be seconds, meters squared over seconds to the fourth. So when we add these two numbers, uh, the only sig figs that come out of that are the whole number parts. So we're going to add the 0.81 to 10.17. It's actually 1761 is what I got. And that gives me the square root of 10.9861 meters squared second to the fourth. But as I said, after the decimal, none of those digits are significant. Now I got to take the square root of that. And what I see is that I only have two sig figs, which is really the most important point, is exactly how many sig figs do I have after I take the square root. We can see I'm taking the square root of a number that has two sig figs, so this number of sig figs should be 2. And the answer is 3.31 meters per second is the total acceleration, and the 1 is not significant. I'll call that a tote just to fit it in there. So that's the magnitude of this vector. The phi, on the other hand, the phi is equal to the inverse tangent of opposite, which is 0.900, over adjacent, which is 3.19. Notice here we only have two sig figs in the numerator and two sig figs in the denominator. I'll hit shift tangent inverse, zero point 0.9 divided by 3.19, close parentheses, and that gives me 15.8 degrees. So we would roughly call that 16 degrees. So this vector is 3.3 meters per second every second at 16 degrees from straight ahead towards the center of the circle. Okay, so now we have essentially all the things we need to actually compute what the, or to actually know what the vector acceleration was. Anybody have any questions on that?
Yeah, when you were underneath your square root, how did you get four decimal places after the decimal when you only had three in both of the two numbers you were adding?
Oh, yeah, that was some sleight of hand. Specifically, I really had 1761 in that spot. I just chose not to write it until after the fact.
Oh,
So
okay. I
that
was I
yeah.
was very worried that I had missed something.
No, it wasn't you, it was me. Sorry about that. I do that a little bit because I really only needed the one non-sig fig, but I threw it in there at the last second, so I apologize. I should have been more clear about it. Anybody else have any questions? That's a good question. I like it when we have those because those are easy to solve and it's no big deal. All right, I'm going to move on to the next example, and this is section 5.6, velocity-dependent forces, drag, and terminal velocity. So, in general, what we've discovered over, centuries since studying motion is that the drag force, the air resistance, if you will, is almost always either proportional to the velocity or proportional to the velocity squared. Uh, I've noticed a little bit that when we're dealing, for instance, with a very, very dense fluid, for instance, not talking about people and cars driving through the air, but considering, for instance, submarines underwater, then it's much more likely that the drag force would be proportional to the square of the velocity instead of the velocity. That being said, there's instances where it goes the other way as well. So in this case, I'm just going to point out a solution for the case where the velocity is, or where the drag force is proportional to the velocity. Specifically, we're doing more or less the derivation that they do, and then asking what is the answer to this. In other words, what's the drag force, and so on. So this is example 517. And I'm going to read that to you. Hold on. So it says determine the velocity as a function of time. V of t is equal to question mark. Determine the velocity as a function of time for an object falling vertically from rest when there is a resistive force linearly proportional to v. Take downward as the positive direction. So they're saying the drag force, they're saying the drag force is proportional to just plain v. Okay, and they're asking us to take downward as the positive direction. That helps. So what I'm going to do is imagine an object in free fall, in what was free fall, but now it's a little bit bigger deal. And I'm going to draw it in a coordinate system. And I'm going to draw this as the downward direction as the positive y direction. Now, with that being said, that means the force that points downward is a positive one, and that is mg, because we're assuming this object has a mass m. Now, we're also going to have a drag force, FD, which, to get rid of the proportionality, I'm going to say it's equal to just B times velocity. And as I was telling some of the students at the beginning of class, generally speaking, when they ask you one of these problems, they have to give you B. There is an equation, like I said, I think it was a Navier-Stokes equation, but basically there's an equation that tells you how the drag force is related to the velocity. And generally the drag force is like, it's got some constant. It's got some constant, then it has these cross-sectional areas. So for instance, if you're falling downward and you've got yourself spread out like a scarecrow, but with your arms and legs spread, then the area would be how much paint it takes to cover your face and your whole front side as you're falling down. Whereas if you went head first, it would be just the amount of paint it would take to cover the top of your head, the top of your shoulders, and that sort of thing. So that's what I mean by cross-sectional area. It's also directly related to the density and or viscosity of the fluid that you're dealing with. And then, like I said, it's either V or V squared. But again, they normally have to give you the number in front of the V, but we're going to just pretend like we know it and work from there. Now, if I take the summation of the forces in the y direction is equal to mass times acceleration in the y direction, then what I get is mg minus bv is equal to m dv dt. Okay, now that sounds okay, and that works fine, but it's not necessarily the best way for us to work with it. So what we're going to do is, first off, I'm going to go ahead and multiply through by 1 over m on both sides. And I'm writing this in a different color so you can see multiple steps in one line instead of having to waste so many lines. When that happens, I'm going to get g minus b over m times v is equal to dv dt. And actually, I need a little bit more space between the two, so I'm going to erase that equal symbol, and I'm going to put the equal symbol over here. Now I'm going to multiply both sides by dt. And I'm going to integrate both sides. So I get the integral of g minus b over mv dt is equal to the integral of dv dt, dt. The right-hand side is just the fundamental theorem of calculus, and that is that the integral of a derivative is the original function. So I'm going to take that from t equals 0 to t, and I'm going to say the object, the ball, was dropped. So that's going to go from a velocity v equals 0 to v, specifically v of t is what we're going to be integrating up to in that case. Now we're going to try to go ahead and figure out a way to calculate it. This actually isn't the best way. I just thought of another way. Let me do this. I was thinking of a different technique, but what I'm going to do is I'm going to pull. Yeah, that's what I'll do. I'm going to divide both sides. Let's write this in purple so it looks like something another step. So I'm going to divide both sides by g minus b over m times v times g minus b over m times v. And I think I'll stick with the dt being there. Yeah, that works good. Okay, so when I do this, the g minus b over m v is going to disappear on the left-hand side, and all I'm going to get is dt. But on the right-hand side, I'm going to get dv over g minus b over m v. I apologize for that going off that tangent for a second there. I've since worked that out. That works pretty good. I think I've got everything in place. The m's not missing. Everything's there. So by multiplying by the dt, that just left a dv on the right-hand side, but it left a dt on the left-hand side. Now I'm going to integrate that. But the range of integration I'm going to stick with. So I'm going to say from v equals 0 to v of t, and I'm going to say from t equals 0 to just plain t. And then, of course, this integration on the right is trivial. That's just t. And the integration on the left is a little more complicated. But the way we can deal with it is we can say let u equal g minus b over m times v. Then du would equal negative b over m dv. Okay? So in order for me to fulfill this integration, I need to multiply the dv by negative b over m. And in order to do that, I also need to divide it by negative b over m. So what I'm going to do is I'm going to take negative m over b, which is the same thing as division by negative b over m. And I'm going to multiply this by negative b over m dv divided by u. And now you can see that this quantity is just plain du, and I've taken the limits of integration off of it because I've changed the variable. So I want to leave that without changing it. I'll change it back to u and then put the same limits of integration. I've already handled the limits of integration on the left-hand side, but on the right-hand side, it's pretty easy. We get negative m over b times the integral du over u, and we know the integral of u to the negative 1 is, notice when you try to do the polynomial rule on that, you add 1 and you end up getting 0. That's the thing that reminds me in my head, oh yeah, this is the one that becomes the natural log. So we're going to get instead t equals negative m over b times the natural log of u. And this is where we now plug back in exactly what u is. And I'm also going to go ahead and multiply through by negative b over m. So this is going to be negative bt over m is equal to the natural log of, now we replace the g minus b over m with u, so now I'm putting in the g minus b over m times v in there. Now, the way we solve this equation is we can imagine raising e to the left-hand side power. So I'm going to say e to the negative b over m times t. And I'm going to set that equal to raising the right-hand side, raising e to that power as well. and this is g minus b over m times v. Now, the one thing that I think is the single most important thing about logarithms that you need to know is this little ditty, and that is y equals log base b of x doubly implies, meaning you can go from left to right or right to left, implies x is equal to b to the y power. That's the single most helpful thing that I've ever learned in logarithms. And of course, ln x means log base e. So when I see something like let's transform this left-hand side into, or excuse me, the right-hand side of the blue equation. Let's transform that into the right-hand side of this expression. So we're going to say x is equal to e to the ln of g minus b over m times v. Well, what that means, according to this rule that we had before, is that the y, which was the exponent, ln of g minus b over m times v, is equal to log based e of x. So what we're saying is, what must x be? And that means x can only be what's inside the radical. So in this case, I get e, let's stick to the blue. I get e to the negative b over m times t is equal to g minus b over m times v. That's really the expression we got. Now I have to actually consider the limits of integration, and the limits of integration were from v equals 0 to v of t. So I really need to do that as well. Technically, if I did that first, then it would be e to the negative b over m times t is equal to e to the natural log of, now if I actually considered v of t, it'd be ln of g minus b over m v of t. And then that would be minus the ln of, this time we're just going to say g because v is equal to 0. So this ends up becoming e to the natural ln power of g minus b over m times v of t, all that divided by g, like that. And that's the same thing as we get over here, except now when we take the when we consider what's happening because we're raising e to a ln power, we just get on the right hand side, instead of this, we get a g on the bottom. So we can now say e to the negative b over m times t is equal to 1 minus b v over mg. Now we can solve for velocity, which is really what we're shooting for. We can say this is b over mg times v of t is equal to 1 minus e to the negative b over m times t. And finally, we've got velocity as a function of time is equal to mg divided by b times 1 minus e to the negative bt over m. I'm going to change that to a square bracket, and that is the actual velocity as a function of time for this particular problem. And if we consider what happens as t approaches infinity, we could see that the limit as t approaches infinity, since this e is raised to a negative b over m times t power, then that means it's going to go to 0, so that you can see the limit of v of t as t approaches infinity is just mg over B. And that is equal to what we'd say V terminal. So that means V terminal is equal to mg over B. And if you wanted to actually graph it, what this function would look like is it's approaching mg over B asymptotically. That's the actual graph of it, but we have now the function as well as the terminal velocity. So, anybody have any questions on that?
Did we ever actually establish what B was for the number, though?
Yeah, that's what I'm telling you is again the B they'd actually have to give it to you, but in this case you're able to work it in terms of a B and then it applies to any physical problem in which you're given B. You just have to plug V in, or it could be applied in the case where you're doing an experiment and you've determined experimentally what B is, you could plug that in. I also mentioned when they could actually make a problem where they say if the drag force on a certain object is, 8 newtons when the velocity is 3 meters per second, what is the terminal velocity? If that was the case, if you literally said the drag force was 8 newtons when the velocity was 3 meters per second, then that says the 8 newtons, which is FD, the drag force, is equal to B times the 3 meters per second, which is the velocity. So if you just divide 8 by 3, you then have B, and then you could plug it in this formula. That's the way it's often done. So they'll pull a little sort of trick in that they'll give you some information that's enough to figure out what B is, but they're not going to just tell you B. Does that help?
Yeah, the main one I remember from the practice test was say they just say they instead of giving you the drag for or the B, they just say the drag force is proportional to V. So,
Yeah, that I'll have to look that one up because it seems unreasonable if they just gave you that.
I mean, they give you like other stuff too, but they don't give you B
Yeah,
specific.
I'll double check. It might be something that allows you to solve for B, but I'll look for that. But feel free to send me a text with a photograph of it, just in case I don't remember, and
Okay.
I'll look it out up and see what I can find out for you. And also, I'll probably send an announcement to everybody because you asked it during class, and I'm sure it'll help everybody. Okay,
All right. Thank you.
thanks, Colin. Appreciate that. Anybody else have any questions? All right, we've completely finished chapter 5 now. So we're going on to chapter 6. And chapter 6 is on gravitation and Newton synthesis. Now, I think I mentioned, let me double check my notes real quick. Not there, not there. Oh, there it is. Yes, I remember doing this problem right here, 5-9, where we calculated the acceleration due to gravity two different ways. One was us imagining, like Newton did, that the acceleration at one Earth radius, which is the acceleration at the surface of the Earth, is 9.80 meters per second every second. And he wondered at the distance the moon was, which is 60 Earth radii from the center of the Earth, what is the acceleration up there? And he said if the force that actually is attracting the moon to the sun goes like 1/distance squared, then he'd expect the acceleration to fall as 1/distance squared. And since the distance is 60 times bigger, you would have to take 9.8 and divide it by 60 squared, which is 3,600. If you divide 9.80 by 3,600, you get 0.00272 meters per second every second. Then, in this example, we were asked to calculate the acceleration of the moon, and they gave us the radius of the orbit of the moon, which is 384,000 kilometers, which they expect us to use in meters. So that's 3.84 times 10 to the eighth meters. And they also said the period of the moon's orbit is 27.3 days. if you assume a circular orbit, then the velocity has to be the circumference divided by the period. So we calculated the circumference divided by the period and got a velocity of 1,023 meters per second. Then we calculated v squared over r, and that gave us 0.00272, which is exactly the figure we got. That's exactly the calculation that Newton conducted. And at that point, Newton was the only person on planet Earth that knew exactly why the planets orbit the sun and why various moons orbit their planets and so on and so forth. So it was a really big deal. That being said, Newton was still bothered by it because he knew that he couldn't understand a reason or a way by which the Earth could reach out and pull on the moon when there's nothing physically touching both the Earth and the moon. That's called action at a distance, and it was a problem. But he was also smart enough to not let that handcuff him because he could still go on the assumption that the force of gravity is a 1 over r squared force, and he could work out what other factors it depended on. And when he did that, he came up with a law of gravity. And with that law of gravity, he was able to make a lot of predictions and solve a lot of physical problems. So, what he ultimately found was that the force of gravity was proportional to the product of the masses, so m1 and times m2, and it was inversely proportional to the square of the distance between them. So if you imagine 2 point masses, m1 and m2, like they're infinitesimal particles, then the force would be directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And since we didn't have vectors at that time, he had to specify some way in which we'd understand the direction. And the way he came up with was if you drew a line from the point particle mass m1 to the point particle mass m2, the force would be attractive and would be parallel to that line connecting them. Now, if they weren't two particles, they were actually physical bodies that had some physical dimension to them, then what you'd have to do is find the center of mass of m1 and the center of mass of m2 and draw a line connecting those 2 points, and the force of attraction would be parallel to that line. So that's what he was able to do, and that's what he told us. After a bit of experiment, and your book explains the experiment, we can do like we did in high school algebra 1 and high school algebra 2. We switch from proportional to equals by making an equation and adding a constant. So to go from that little fish looking symbol to an actual equals, we'd say F is equal to some constant. And we actually called that constant or label that constant with a capital G. And it's called the gravitational constant of the universe. And it's G times M1 times M2 over R squared, where G, get this, it's a really, really teeny number. It's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That is the actual constant, the universal gravitational constant, or the gravitational constant of the universe. Notice it's 0, a decimal point, 10 zeros, and then 667. So if you're even going to get a force of 1 Newton out of it, the product of the two masses has to be at least equal to 10 to the 12th. So you'd have to have two things that are like a million kilometers times a million, or excuse me, a million kilograms times a million kilograms. And then they'd have to be at least, or excuse me, closer than 1 meter apart. Okay, because if it was bigger than a meter, you'd start cutting it down again to less than a Newton of force. So it is a monumentally, quote unquote, weak force. Just to sure that up for you, let me show you the Coulomb force, F Coulomb. This is the force of attraction and repulsion for two charges. That turns out to be K, and instead of M1 times M2, it's Q1 times Q2, where Q1 and Q2 are the charge, something measured in coulombs that you'll learn about later, and inversely proportional to the square of the distance between them. Again, it acts along that line connecting the center of charge of Q1 and Q2. So it's exactly like Newton's law of gravity. But here's the weird part. K is 9.0 times 10 to the ninth, and that's Newton meters squared per coulomb squared. So the other one was a decimal point followed by 10 zeros followed by a 667, whereas this one's 9 billion. So just comparing those two factors alone, you would think that the Coulomb force is 10 to the 20th power stronger. It actually is even worse than that. If you wanted to compare, for instance, the gravitational attraction between the proton and the electron in the hydrogen atom, due to the gravitational force, and then do it again for the Coulomb force, what you'd find is the Coulomb force is about 10 to the 40th power stronger than the gravitational force. So that's a really big deal. Again, Newton knew these problems regarding the action at a distance, but he could solve a lot of physical problems. And in fact, he did. He went on and showed, for instance, why the planets were spherical. And he went on and showed basically that anytime you have a spherical mass distribution, you can pretend like it's a point particle with all its mass located at the center of mass of the point particle of the sphere. In other words, at the center of the sphere. So that was monumental. He was also able to prove Kepler's three laws of planetary motion, and I'm going to go over those now. All four of these things, Newton's law of gravity and the three laws of Kepler, are quote unquote laws, and they're, whole chapters and whole sections of chapters are named after them. So I want to remind you folks that whenever you're in a physical science and they have a whole section dedicated to some equation or some principle or some law, then it's probably a good idea to take time to go ahead and memorize that and keep that memorized for the entirety of the course, because a lot of times teachers think they're doing you a really good favor by throwing a question on the test and saying, state Kepler's three laws of planetary motion in order and label each one Kepler 1, Kepler 2, Kepler 3. That's supposed to be a chucker question that's a freebie. I have personally in the past not taken the time to memorize certain things like that and been bitten by what was supposed to be a really nice gift from my teacher. So I want you guys to benefit from my screw ups and not make the same mistake. So let me go ahead and go over those. I just mentioned Newton's law of gravity. He basically said that the force of gravitational attraction is directly proportional to the product of the masses and inversely proportional to the square of the distance between them, and that the force of attraction acts along the line connecting the two masses via their centers of mass. So that gives you not only the magnitude but also the direction for the force. The Kepler's law, I'm going to give it to you in my own way, but I suggest you read it from the book because I'm not going to take the time to write a lot of sentences. But I'm going to start off by saying Kepler's first law. I'm just going to call it K1. And what Kepler's first law was is it was a big shot over the bow for not only Copernicus but also Aristotle, because remember, Copernicus comes in and says, hey, we've sort of lost ourselves from what Aristotle taught us. We have epicycles and deference and equipoints and all these crazy things, and the whole system that we have to use to calculate where the planets will be 3 years from now and stuff like that has become really onerous and awful. And it's actually a lot simpler if we just say, let's imagine that the Earth is not the center of the universe, that in fact the sun is, and that the other planets, including the Earth, orbit around it. In so doing, he discovered that the orbit of Mercury having the shortest period was obvious in this model, and then the fact that Venus had the second shortest orbit made it equally obvious, and so on and so forth. In doing that, he went back to using perfectly circular orbits, which turned out to be completely wrong. Okay, but that being said, with Copernicus's model compared to the Ptolemaic model, the two models were equally successful. Now, if you use Occam's razor, you would say we obviously need to throw out the Ptolemaic model because the Ptolemaic model required way too much crap that we hadn't verified. The basic premise of Occam's razor is the idea that uh, requires the largest number or the most things that haven't been verified is the most complicated model, and you should probably discard that until unless you find some way to justify it. So obviously Copernicus's model would win out the day, but it turns out neither one of them are very good. Kepler comes along and tries to fit his own model. That doesn't work. And then ultimately he just throws it all out and comes up with his own, not the one that he had been jockeying for, but a whole new one. And the first one says that the planets orbit the sun in elliptical orbits with the sun at one foci or one focal point. So if you imagine drawing a circle, you could, for instance, drive a nail in a piece of plywood, tie a string to it, tie a pin to the other end of the string, and then pull the string taut and work real hard to keep your pin perpendicular to the string. And then you would trace out a circle and it would come out pretty good. Well, an ellipse can be done sort of the same way, but you need two nails. So we could imagine, for instance, putting two nails in a piece of plywood like this, and instead of tying a string to just one of the nails, we're going to tie a string, for instance, to both of the nails, one end to one string, one end to one nail and the other end to the other nail. And then I'm going to imagine sticking a pin in there to keep it taut, so you can imagine the pins right there. Now, if you allowed this to hold the string taut, then it would trace out a shape something like this. Okay, that's not the best in the world, but it's not horrible, I guess. So that is sort of a elliptical orbit, if you will, and each of those nails represent focal points for the ellipse. So the sun could actually be at either one of them. We'll choose one in a second when I go to use this as an example. But that's what an ellipse looks like, and that's also a way you could make it. If you actually were to measure along this distance from here to here is called the major axis. Now, we use the phrase major axis as an object or a thing, and you can actually imagine it being this line right here, but it also represents the distance from one end of the orbit to the other. Additionally, we could imagine another object from this end to this end, and I bet you can all guess what this is going to be called. Anybody? I'll give you a hint. The second word is axis. The first letter of the first word is M. It's the minor axis. Okay? Now, I want to point out something here. Our planet could be right here, for instance, and at that time, this position is called perihelion. So we're going to imagine the sun is here, in which case this position is perihelion. And that distance is also called perihelion. So we'll use the phrase perihelion, and it represents the position, but it also represents the distance from the center of the sun to the center of the planet when the planet is closest to the sun. If it was something orbiting our Earth, then it would be perigee, for the Earth being recognized as Geos, and helion because the sun is recognized as Helios. Now we can also say that the distance from here to here is another quantity, and that's called aphelion. So in this case, we're going to say this is aphelion, But again, that's a position as well as a number. Now, if you look at the perihelion distance and the aphelion distance, if you added them together, what would you get? Can anybody tell me what the name of the quantity would be if you add the perihelion distance to the aphelion distance?
The
Any,
width?
what's that?
I just said the width.
Okay,
It's
yeah, so
technically the width of the
it is the width, but we
ellipse.
wrote another name for that other than the width. It's still
The
on the
major
diagram. There
axis?
you go. Equals the major axis, which remember is not only a thing, but it's also a distance. Now, here's the neat thing. If you take the average of those two, remember you're taking the average of the shortest distance between the sun and the planet and the longest distance between the sun and the planet. So, in some sense, when you average those two, you're actually getting an average distance between the sun and the Earth. Does that make sense? So if we were to put this dead center, which looks like I'm going to be right about here. Actually, I meant to write that in black. Okay. Then this distance from here to here is the quantity A, and it's called the semi-major axis. And you can imagine if you split the minor axis in half, you'd have a semi-minor axis as well. But the main thing is because the average of the aphelion plus the perihelion distance is the semi-major axis, you can use the word semi-major axis or the word average distance for the planet, and they mean the same thing. So that's one of the ways we can ask you questions about orbits and not explicitly tell you, hey, we're asking for the semi-major axis, or hey, we're asking for the average distance. We can refer to one and you should know it's the other, and we can refer to the other and know it's the first one. So
Uh,
that, go
was
ahead.
the semi-major supposed to be halfway through the major axis, or is it supposed to be halfway
Yes.
through the aphelion?
Yes, it's halfway through the major axis. I tried to draw that dead center between the focal points.
All right.
So this one's also A, like that. Okay. Now that's Kepler's first law, and it's a big deal because ellipse is a bastardized version of a circle. And remember Aristotle using these axioms that seemed obvious to him, like the heavens are perfect, ergo nothing in the heavens can be any shape other than a sphere or a circle, because those are the perfect shapes. That seems kind of quaint and ridiculous to us, but that was what they were working with. Okay, so this is a big smack in Aristotle's face and Copernicus's, because Copernicus wanted us to get back to Aristotle. Now, the second rule, Kepler's second law, says that the planets sweep out equal areas in equal time. Okay, what does that mean? Well, I'm going to try to draw an ellipse again. I'm going to draw it from here to 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, something like that. So I'm going to try to draw it like this, something like that. That looks decent enough, I guess. Okay. Now, what do we mean by sweeps out equal areas in equal time? Well, what we mean is if you imagine that a line connecting the center of the Earth to the center of the planet uh, actually existed, then you'd say, through what angle did that line move? So you could, for instance, draw right here and say, this is day 0, and then right here and say that this is day 30. Actually, let me make the day 0 a little closer. I'm going to get rid of that other day mark just to make it a little bit more symmetric, if you will. So this is what we mean when we say sweep out equal areas in equal time. I just found an area, and that area is sort of like the amount of cheese that it would take to cover that slice of pizza. Notice how it looks sort of like a slice of pizza? That's the area we're talking about. Now, if you imagine the same planet at the other end of the orbit, then that slice of pizza is going to be long. And if we want it to be the same area, it'd have to be long and very narrow. So what we can see is that the path traveled during 30 days on this end was this really long black path. Whereas if this other end was also day 0 and day 30, meaning again it took 30 days to complete this, then in this case, when this planet is really far from the sun, it goes very slowly. And that was really what he was talking about. The planets actually speed up and slow down. They speed up when they're getting close to the planet, and they reach their max speed when they're at their closest position. And then they start to slow back down as they get further and further away, and they reach their minimum speed when they're at their farthest distance, i.e., aphelion. Okay, so they're at fastest at perihelion and at the slowest at aphelion. So that was another smack in the face because Aristotle said that the heavens are immutable, and that means they can't change. And his reasoning was, if something in the heavens went from going one speed to another, then clearly they went from going the perfect speed to a non-perfect speed, or they were originally going a non-perfect speed and changed to go to a perfect speed. Both of those are totally unacceptable. So this too was a smack in Aristotle's face. So it was a really big deal. Newton was able to prove every one of these just using his equation of motion, his equation for gravity. Now, there's a third law as well, and you've probably learned a little bit about this in lab already, or at least seen it. So, in this case, what he said is the square of the period of an orbit is proportional to the cube of the semi-major axis. Notice that's the word we just finished working with above. So the symbol we give for period is T, and the symbol we give for semi-major axis is A. So what we're saying is A cubed is proportional to T squared. And of course, like we did before, if we want to make that into an equation, we'd say A cubed is equal to some constant K times T squared. By the way, if you can't remember this, remember there's a place where we celebrate New Year's Day in New York City. Does anybody recall where that is in New York City that we ring in the New Year? Not us personally, but the people that come on TV that are evidently more important than us.
Times Square.
Times Square, exactly. And notice the time, which is a period, the amount of time it takes to go from one point in the orbit to that same point again. That time is squared in this equation. So that helps you remember not only the fact that it's a time, but also that the exponent for the of 2 goes on the time. And in fact, you know some data about one of these. If we actually were to use, for instance, the semi-major axis in astronomical units, and we use the period in Earth years, then we could use the data we know about the Earth. For instance, the average distance between the Sun and the Earth is defined to be 1 astronomical unit. And does anybody know how long it takes to go from, let's say, this point in the Earth's orbit to this point again? Does anybody know what amount of time that takes?
365 days.
Exactly, which is 1 year. So this would be 1 AU, and this would be 1 year. So if you plug in, I don't know why I wrote a T there, but that's what I did. Anyways, so if we wrote in 1 year for the T and 1 astronomical unit for the A, what must K be?
One.
Exactly. So in that case, if we use the units of astronomical units in years, K is going to have to be equal to 1. That also happens to be an extra credit problem that you guys can work out because when you set Newton's law of gravity, G times the mass of the planet times the mass of the sun over, notice I'm using A here for the semi-major axis, which is sort of like a radius. So that's A squared. If I set that equal to the centripetal acceleration, which is mv squared over, again, A, okay, then what you can see immediately is this mass and this mass cancel out, and this exponent of 2 and this A cancel out. Now, if you assume the orbit's more like a circle than an ellipse, because it turns out these ellipses are very much circular. Like if you had the orbit of Pluto, which is the most elliptical one, even though it's not literally considered a planet anymore, if you had the orbit of Pluto right next to about the same size circle, without quite a bit of measurement, you wouldn't be able to tell which one's the circle and which one's the ellipse, even though Pluto's orbit's the most elliptical one. So they really are close to circular. However, when you have a circular orbit, that means the velocity has to be the circumference, which is 2 pi. Remember, I'm using A for the radius over the period, and remember, I'm using T for that. So now I get G times the mass of the sun, circle with a dot in it, over A is equal to 4 pi squared A squared over T squared. And sure enough, you can solve that, and what you get is A cubed is equal to G times the mass of the sun over 4 pi squared times t squared. So if you take the value of g, the value of m, and 4 pi squared and put that in SI units and then change it to units of cubic meter or cubic astronomical units per year squared, you can see that it equals 1. That's the extra credit problem I gave you as well. So now we have Kepler's 3 laws. I will tell you that the way he found out this law, and this is why I was referring to what you've done in lab, he found that you could plot period and semi-major axis on the axes and put different exponents on it. And he kept doing that until he got exponents that gave him a straight line. And that happened when the exponent on the A was 3 and the exponent on the T was 2. And then he did a curve fit, and lo and behold, that was his proof that the square of the period is proportional to the cube of the semi-major axis. So that's how that was done. Anybody have any questions on that? All right, so that's Kepler's 3 laws. Now, we're going to do more problems with this next time, but I wanted to do at least something. So one thing I told you guys you can do, another extra credit problem, is you can calculate the Coulomb force of attraction between the proton and the electron of the atom, and you can calculate the gravitational force of attraction between the proton and the electron and the hydrogen atom. And then you can divide the Coulomb force by the gravitational force and see that it indeed gets you 10 to the 40th roughly. It's actually even bigger than that. That's another extra credit question you can do. But if you want to do that, you need to let me know, because I don't normally assign that for the 241. I normally assign that for the 242. But let's work another problem. There's a conceptual problem or an estimate problem in example 6.1. So let's say example 6-1. It says a 50 kilogram person and a 70 kilogram person are sitting on a bench close to each other. Estimate the magnitude of the gravitational force each exerts on the other. So what we know is F is equal to G M1 M2 over R squared. 50 kilogram and a 70 kilogram person are pretty small, okay, especially that 50 kilogram one. That's like well, it's just small. I'm 110 kilograms, so it's way smaller than me. That being said, that means the center of mass of the two people can't really be any closer than maybe 20 centimeters, because best case scenario, each person's like 20 centimeters wide, which is still a little too narrow, to be honest with you. But if you really forced them in together, you could get those center masses about that close, and that would sort of max out the force. So what we can do is say 10 to the negative 11th, which is what the gravitational constant is approximately. We can say 50, 70, and then we're going to divide that by 0.2 squared. And what you get when you do that is 10 to the negative 11th times 50 times 60 divided by zero point 0.2 squared. And that gives you 7.5 times 10 to the negative 1, 2, 3, 4, 5, 6, 7 times 10 to the negative 7 newtons. So you can see already that that is really small. In terms of everyday life, if you want to measure the newtons, the force on something, we can maybe get 2 or 3 decimal places on newtons, but that's about it. So this is not really a measurable quantity unless you really wanted to pull out some fancy stuff that we use at the atomic level. So yeah, that's a really small force. Anybody have any questions on that? All right. Another neat example is example 6.2. And this one, it says, what is the force of gravity acting on a 2,000 kilogram spacecraft when it orbits 2 Earth radii from Earth's center? That is, it stays a distance RE equals 6,380 kilometers above the Earth's surface. The mass of the Earth is 5.98 times 10 to the 24th kilograms. Assume a circular orbit. So, what we have here is a Earth that has a radius RE. And actually, I'm going to use the symbols that we use in astronomy because it works a little better, a little nicer. So we would call this RE. And then we're going to say this is 2 times the radius of the Earth. And that's like the space shuttle or something like that. What we want to know is, what is the force of gravity acting on a 2,000 kilogram shuttle uh, when it orbits 2 Earth radii from the Earth's center. And Earth's radius, by the way, is 6,380 kilometers. So the force of gravity is equal to the object's weight, which is supposed to be mg. So the force of gravity at 2re would equal, notice because F, gravity, is equal to G times the mass of the space shuttle times the mass of the Earth divided by the distance squared. We can see if we let that equal to mg, over r squared, we can see that the m cancels out, and that tells us that g, gravitational acceleration, the 9.80, is supposed to be g times the mass of the Earth divided by the radius of the Earth squared. If we go at R equal to RE, R for the Earth, then G would equal 1/4 G at the surface. So we could say we could say 19,600 newtons equals mg at the radius of the Earth, but that's being 2,000 times 9.8 gives me 19,600. But if we did the same thing, we would have to divide that by 4, and that would be 4,900 newtons equals mg at 2 times the Earth radius. So that's really what it's going to be, is about 4,900 newtons. There's a lot of different ways you can solve this. That's just one of the ways that I pointed out for you. You guys are free to go. Remember, we have a test that has to be done by Saturday. So get that done. Make sure you chat me your first and last name if you haven't already. I'll wait for the last person to leave in case anybody has any questions. But you're free to go. And thanks again for coming, everybody.
I have a question on your final answer
Yes.
for the 4,900 newtons equals. Is that supposed to be M at or MG
Oh,
at?
that was supposed to be MG. I wrote A twice. Oh,
Okay.
man. I don't know what's going on with me, but thank you for catching that.
Yeah, thank you.
Oh, I got to erase that before I upload this thing. Anybody else have any questions?
Hey, I have a quick question.
Mm-hmm.
So in regards to the email that you sent about your proctored exams, I just wanted to double check them good to go for Wednesday at 2 p.m. I sent you an email, but I just wanted to
Yeah.
make sure them.
Yeah, I saw your email coming today. That you're the person that you're Ryan, right?
No, I'm John.
John. Oh, okay. Actually, no, I just saw Ryan up here. Maybe that's why. You're the person that sent me one and asked for 3, but I told you I couldn't do it at 3.
No,
Okay, cool.
no, I requested to do 2 p.m. for Wednesday. That's one of the exam times that you mentioned.
Yeah, that's great. I appreciate that, and I will put you down as that time. Let me write this down right here.
Okay. And I believe I'm not sure if he told you about my friend as well, Aiden Johnson. He's in this class as well, but he's doing the same time.
Okay, that's cool.
Cool.
Can you
Sounds
also put me down for that time as well? I tried to get to you in an email, but for some reason, government computers don't like school email addresses.
Gotcha. So this is Jaden and
Yes, it is.
Aiden. Jaedyn and Aiden Aidan, maybe something like that.
yeah. And then also John.
And John too. Oh,
Yep.
John Pang, I already got that one. Gotcha.
Thank
All
you
right,
very
cool.
much. I do
No
Thank you.
problem.
appreciate it.
Thank you. I look forward to meeting you guys or folks, excuse me.
Yeah.
I use the non-gendered guy word, but still.
Yeah, no worries. Actually, one last thing for
Yes, sir.
I know you mentioned this last Wednesday in regards to the practice exams. You mentioned something about the practice exams, like 80 or 90% of it is gonna be either the exact same or like same kind of like concept.
It's literally going to be the same questions
Okay.
as appear in those practice tests.
Okay, cool. Yep.
Because I haven't done that. I haven't added any other ones in a couple decades.
Okay, no worries. Just wanted to double check. Thank you.
No problem. You're welcome.
Yep, have a good one.
You too.
Thank you again. I appreciate it.
No problem. Thank you, Jaden.
I also
Hello.
had a. Oh, I'm
Oh,
sorry.
go
You
ahead.
go.
Mine's real quick. It's
Gotcha.
Ryan. I was able to take my test on Saturday, so we got no issues there.
Oh, good. Appreciate that, Ryan.
Thank you.
All right. Have a good one, bub.
You too.
I sent you an email earlier,
Mm-hmm.
asking for the 9:30 on Wednesday. I
Yeah.
just wanted to double check if that was okay.
Yeah, that shouldn't be a problem at all. This is James McCormick,
Yes.
and 9:30. You say Wednesday?
Yes.
Yeah, no problem. Appreciate
Awesome.
that.
Thank you so much.
All right. Have a good one, bub.
You too.
Bye-bye. So it looks like we're all done. I'm going to stop sharing. And thanks again, everyone, for coming. Bye bye.